I'll talk very slowly. We'll just give everyone else a little bit of a chance to come on to the meet. Okay, well, again, thank you for joining us. We're coming to the end of these series of lectures now, and particularly for those of you who've been to lots of them, I really appreciate that. As always, we've been really lucky with the people we've been able to get. In this case, we've got Professor Mark Zwolinski from Southampton, and we're going to be looking at computer science. It's worth saying Southampton's one of the sort of top destinations in the UK for that subject. We've tried to do that as much as possible and focus on those institutions that have strengths in the areas that we bring in. So hopefully this will be a really insightful and interesting conversation for you all. As always, before I hand over to Mark, our main thing, if you have a question that you want me to put to Mark at the end of the session, please add it to the chat function. You can do this at any time. If you feel you don't want to add it to the chat, you could email myself or Miss Shazza directly if you feel that will be easier, and we'll try and pick them up that way. But easy enough just to pop everything into the chat, and we'll do our best to answer them at the end. The presentation will be about half an hour to 40 minutes, and we'll try and end today just before the hour, about 5 to. So I'll try and bring things to a close about 5 to the hour. Okay, so without any further ado, I'm going to hand over to Mark now, and he can tell you a bit more about computer science at Southampton, and obviously the computer science in general. Mark.
Hi. So yeah, as Joe said, I'm professor in the School of Electronics and Computer Science at Southampton. Now that's significant. I'll talk about why the fact that we're a School of Electronics and Computer Science is sort of relevant to this, because I'm going to talk a bit. Some of this is really going to be electronic engineering as much as computer science. It kind of crosses over between the two. There's a few people here. I did say, actually, if people have immediate things they don't understand, you really want to ask me a question that you think I'd best answer on the spot, by all means put it in the chat. I've done this talk a few times in the past, so I kind of know how long it takes, and there is time, I think, to interrupt. So, but I'm conscious of the time as well. I don't want to spend too long on this. I guess it's 5 o'clock in Malaysia. It's 9 o'clock in the morning here in Britain. It's rather grey and overcast because it's still really winter here. It's about 7 or 8 degrees outside. So, which is why I've got a jumper on because it's a bit cold. Anyway, let me press on. What I want to talk about is sort of next generation of computing, if you like, and how we can have very powerful computers that are not particularly expensive. And what I'm going to do is give you a little bit of history about how computers have evolved over the past 60 years or so. And then something about how computers work in general, a little bit about some other technologies, silicon chips, and how they differ from computers. And then leading to the point where we actually sort of bring the two things together, the development of computer chips. I mean, of course, computers themselves are chips, are silicon chips, but what I want to explain is how we can have sort of specialized chips that work with general purpose computers and produce a lot of computer power. So let's start off, right at the beginning of all of this. I'm juggling screens a bit here. I apologize. I've done loads and loads of talks over the past few months using Microsoft Teams. This is the first one I've done using Zoom. So if I'm a bit clumsy with the technology, I apologize. Anyway, so what do I mean by a supercomputer? Now, computing power has increased exponentially in the past 60 years. And the word exponentially is misused a lot. People talk about a big increase as being exponential growth. Here, I literally mean exponentially in the mathematical sense of the word. The power of computers has doubled every 18 months or so for the past, maybe not quite 60 years, but certainly 50 years. So a supercomputer is often seen as a big machine that sits in large cabinets in an air-conditioned room. And they're very expensive and they're very specialized. So this is a picture from about 60 years ago. This was an IBM stretch computer. There's a guy sitting there with a console, lots of racks behind. And that sort of picture hasn't changed particularly in all of this time. If you saw what Google have or Facebook have or any of these big tech companies, they have rooms that look very much like this. The difference is the power's changed. The computing power in that room is probably less than on your mobile phone. I'm not kidding. It really is a huge amount of computer power that you now have compared with what was available at that time. And indeed, at about that time, people predicted, somebody from IBM said, the world will only need 4 computers. Well, you can tell how wrong that has been. And I'll come back to that later on. So moving on 10 years or so, this was a Cray computer. This is about 3 meters tall. It looks like a bench. It is a bench. You can sit on that circle that's going around the outside. It's circular to cut down the connections within the computer to make the distance shorter. Again, that was very futuristic at the time. It looks fairly feeble now compared with what computers can do. So one measure of processor power is the clock speed. It's only one measure, and it's not a particularly good measure, but just to give you an idea of how things have increased. In the 1970s, this kind of machine, the Cray, had a clock speed in the region of hundreds of kilohertz. Computers now have clock speeds of 4 gigahertz or so. But there's an interesting story behind that. I say 4 gigahertz in 2003, which is probably just before most of you were born. But in truth, computer speeds haven't increased really in that time. And again, I'll say a little bit about that in a moment. But another measure of computer power is what are called MIPS, millions of instructions per second. So that IBM Stretch, that first picture I showed, in 1960 had a power of about 1.2 MIPS. The Cray 1, the circular computer, in 1975 had a power of 160 MIPS. That's about 150 times as much power. The Raspberry Pi, which is a tiny little computer, but again, sort of similar in power to your mobile phone, has nearly 5,000 MIPS. So not only is your mobile phone more powerful than that room full of computing, it has about the power of 4,000 or 5,000 of those machines. Okay, so far more power in your pocket than existed in the world throughout the 1960s. Now, you've probably heard of Moore's law. The engineer, founder of Intel, said in, I think, the 1970s, computer power doubles every 2 years. He then changed that to every 1.5 years. And there are different ways you can measure this. So this is a slightly older slide. It's from a few years ago. The green line shows the number of transistors on a chip. And if you look at the y-axis down the left-hand side, that is going up in powers of 10. So it is an exponential increase. And so the green line looks straight, but actually it's an exponential curve. The dark blue line below it is the clock speed. And as you can see, as I just said, it levels off. In about 2003, the clock speed hit about 4 gigahertz for the most powerful machines and then stopped. There are other things you can measure. The power blue line is power as in electrical power that is consumed by computers. The purple line is performance per clock cycle. That's not so important for the purposes of this talk. So what's happened over the past years, basically during your lifetimes, is that computers haven't got faster, but they've got bigger in terms of transistors. And so what you have now are computers that consist of multiple cores. And if you look at I'm doing this on a MacBook. I'm talking to you from a MacBook. It's got an Intel i5, which has got 8 cores. And so this is a 4-core chip from Intel. And you can see that these images are kind of mirrored. Okay, so we've got the left and the right are mirrors of each other. And then within the two halves, they're mirrors. And so we really have 4 identical computers. Most of the transistors there, most of the area is actually memory. It's cache. And you can see the level 2 cache is a huge area, nearly probably about a third of the chip. So we've got 4 times the computing power there, but have we actually got 4 times the performance? Now, the challenge here is that we've only got 4 times the performance for a specific task if we can write parallel programs. And the truth is, people have been struggling with parallel programming for probably 50 years and have never really cracked it. There are all sorts of things you can do, but it's very, very difficult to write a program that will scale, that if you put 4 processors on solving a particular program, doing a mathematical calculation, it won't necessarily go 4 times as fast, and you hit limits. And that's to do with communications, but that's kind of off the topic for today. One way to increase power is to use what are called coprocessors. So we can move some of the computation from the main computer and put it onto what's called a coprocessor. Now, this has been standard for floating point calculations, in other words, using real numbers, non-integer numbers, for many, many years. And I'm sure you're all aware that many computers now have graphics cards. The idea of a graphics card is you do all the processing on images and on films and so on a separate graphics card rather than on the main processor. The graphics card is basically an array of very small processors. And because you're doing the same calculation on every pixel or every set of pixels in an image, you can do lots of things in parallel. And people are now starting to exploit these graphics cards for other things, because in fact, the graphics cards themselves are quite powerful computers. And many of the top 500 computers in the world, the most powerful computers in the world, use these graphics cards now for other calculations. So there's a kind of a league table, a top 500 of computers that you can look up, and this is updated every 6 months. And the computing power there is astonishing. And you know, computers that have hundreds of thousands of processors. But as I say, they're now using these graphics.
Oh, I don't know if we're all experiencing the same. We've lost
Yep, we've lost.
Professor Zwolinski. Well, we'll give him a chance. I'm sure he will return back in a minute. So if we're all just patient, I'm sure he will. Has he dropped out of the meeting completely, Shazza?
Yes, he did.
Yeah, okay, so I imagine he'll rejoin and then we'll be able to pick up where he left off. So we just give him a little bit of time to come back in. As always, do remember to stick stuff in the chat. Otherwise, it's my questions it'll be getting. I'm sure you all know far more about this topic than I do. So please, you know, obviously, this is a real expert in this field. You can really ask him anything at all. So, hi, Mark. Glad to have you back.
I'll mute myself. Sorry, I'm not sure what happened there.
No
Obviously,
problem. You just froze up for a bit there. But if you just pick up from where you were, absolutely fine. We only lost a small amount.
Right. Okay, I'm trying to find the right window to share. Just bear with me 1 second.
No problem.
Why has this? Oh, sorry. Right, I can't see for looking. It was okay. Right. Okay. Can you? Oh, hang on. I haven't done share. Right. Try and get this. Get myself together. Right. Okay. You can see me again. Okay. Right. So what I was saying was, I'm not sure at what point I dropped. I was saying that many of the top 500 computers these days use these graphics cards to make calculations a lot faster. So a graphics card is basically an array of small computers. So this is an image from NVIDIA that some of you may have heard of. It's a very sort of stylized diagram. The little green dots represent the processors, and the blue and the orange represent memory. Basically, a lot of this comes down to memory. You may realize. And so a graphics card has 128, 256, whatever, a large number of small processors. But, and this is really the sort of the nub of the problem, the thing I'm coming to in this talk. There is a basic problem with processors, with microprocessors in general. They are serial. They do one thing after another. You have to program them that way. You write a program in C or Python or Java or whatever. And it's one operation followed by another. And they do one thing at a time. They're limited by shared resources. So this little diagram here shows, you know, the parts of a microprocessor. And they share resources by using this central bus structure, the line going across the middle of the image. I'm trying to find my pointer. Right, this middle line, if you can see, is a bus. It's a shared resource, and only one thing could use it at one time. So microprocessors are generally quite slow, but they can do anything. That's what makes computers powerful, because you can program them to do literally anything you want. Whereas many of the more specialized things, such as these graphics units, are much harder to program. You have to do something that is inherently parallel. You have to do something like image processing, where you're applying the same operation to all the pixels in an image. And therefore, it is something that in making it parallel is easy to do. Now, you can, of course, take that a step further and design your own chips to do various tasks. So if you think of various applications that you may have, consumer electronics, if you've got a set-top box or something like that, or something that controls things in your car, you have specialist chips, because they do one task, and they do one task, but they do it really, really well and really fast. And these are chips are often called application-specific integrated circuits, and they are massively parallel. Now, I've used these words serial and parallel a number of times, and I think this is what's important to realize, is that if you're doing one thing at a time in a serial way, it's slow because you have to wait. Ideally, you want to do everything in parallel, because that's the way of the world. Lots of things happen at the same time. But to produce an ASIC, an application-specific integrated circuit, can take months or even years, and the fabrication takes a while. Now, if I do just stop for 1 second and do a quick sort of commercial break here, if you were to come to Southampton and if you were to study not computer science but electronic engineering, we would get you to design an integrated circuit, an ASIC, in the second year of your program. It's only a small thing. It's done as part of a team. As far as I know, we are the only university in the world that has second-year undergraduates designing ASICs. If you're doing computer science, unfortunately, it's not so easy to do this, but as I will show you, there are ways in which these technologies are converging. So let me sort of continue on that theme for a moment. ASICs have been around a long time. They're just basically silicon chips. So integrated circuits were invented, I guess, in the late 1960s, 50 years ago or so. At about the same time, people realized that producing these specialist chips was slow, expensive, difficult. And people came up with the idea of having an array of gates, called a gate array, rather prosaically, where you have the structure of the chip kind of defined. You've got a whole array of transistors, and basically all the designer has to do is wire those things up. So this is much cheaper because they're standard components. It's much faster because all you're doing is just defining what the wiring is. Okay, a step beyond that is a few years later in the 1980s, what were called field programmable gate arrays were invented. Now, field here doesn't mean take it out to a grassy area and play with it. What it means is the programming, the configuration of this chip can be done away from a factory and can be done on a desktop. And so these FPGAs are used for specialized hardware. They're used for prototyping. I don't know if you can see my face on the screen, but if you can, I'm going to hold up. This is a development board, and I'll show you an image of this in a moment, so I'll try and get it so it doesn't reflect light, which we use for teaching. It costs about $100 US, something like that, maybe slightly more. In the middle of this, there's a black square. That is an FPGA. And I'll come back to that later on, but the point I'm making is that this has no wires connected to it at the moment. I can plug this in through a USB connection into my laptop. I can configure this. I can make it do pretty much whatever I want in terms of an electronic system. So programming FPGAs is a little different to programming programming microprocessors. We have to use specialized languages. And there's all sorts of reasons for this, but languages like C and C++ and Java and Python are not particularly good. Again, this question about doing things in parallel. Now, certain things can't be synthesized. If you've done any programming in any depth with languages like C++, you'll know that you can have constructs like C++ in C++, like linked lists. You can't really have a linked list on a piece of hardware because you can't have something that kind of grows and shrinks dynamically. You can't have bits of hardware that appear and disappear magically. So we tend to use more specialized languages. So there's one language called System Verilog. I teach this to undergraduate students. Again, this is electronic engineering, not computer science. If you look at that, it looks a bit like C or C++. It's not quite the same. 10 years ago or so, I wanted to teach this. I couldn't find a suitable book. So what do you do when you can't find a book? You write one yourself. So that's the image of it. And this is the book for real. Again, if you can see the screen. And I use that for teaching. I'm going to skip the next slide actually and go through it now. These FPGAs are quite powerful chips. You can do a lot of things with them. A few years ago, there was a headline in various financial pages. This was taken from the New York Times, but other newspapers had similar sort of headlines. Intel, you've all heard of Intel, make microprocessors, agrees to buy Altera for $17 billion. Altera is the company that made, or makes, if you like, these FPGAs. There are two big companies. One is called Xilinx, one was called Altera. And so people were sort of speculating, why does a microprocessor company want to go and buy an FPGA company? Why go to do something different? Does Intel just simply have too much money? They don't know what to do with it? Have they got a plan? Well, it seems like they do have a plan, because what we're starting to see, and I'm going to go slightly off topic here and sort of explain some background. These FPGA chips often include a microprocessor on them in their own right. The microprocessors they have are typically ARM. Now, you may not have heard of ARM as a company, but you probably should have done. ARM have sold over 100 microprocessors for every single person on the planet. In other words, probably something getting on for 1 trillion microprocessors. Now, they don't actually sell chips. They sell designs. And the companies they sell the designs to are Samsung and Apple and pretty much everybody you've ever heard of in terms of mobile phones. So your mobile phone almost certainly includes 1 or 2 or 4 or 8 or whatever ARM designs. So ARM is a company based in the UK, based in Cambridge. Many graduates from Southampton University go and work for ARM. They design chips, they design processors, and these are sold to other companies. So Apple say on the back of their devices designed in California. Well, that's sort of true, but the processors themselves are often designed in Cambridge. And so you can use these ARM processors on an FPGA for various functions, and I'll talk about that in a couple of minutes' time. But you can also put the designs of a microprocessor onto the FPGA. You write a model of it in a language, one of the languages I've just been talking about, like Verilog, and you put it onto the FPGA, and so you can experiment with computer architecture. But what we're getting to the point now is that the FPGA, that programmable device, this specialized chip, and the standard Intel or ARM or whatever microprocessor are sitting on the same piece of silicon. And so therefore they can talk to each other very, very easily in principle. They use buses, the communication lines within chips. They can use the PCI Express bus that many of you have heard of, that graphics cards use. But you still need to put that interface on there, and this is actually quite difficult to do. It's quite a lot of work. I've had students trying to do this, and it's, they can spend 3 months just designing that interface before they do anything useful. And so people have developed other languages. Now, I said a few minutes ago, we don't use C and C++ and Java and so on for programming FPGAs. That's actually becoming not true anymore. There are languages called OpenCL that you might have heard of, perhaps for programming graphics cards, are now being used to develop applications on these FPGAs. It's a high-level language. It avoids the low-level Verilog type things. And in principle, anybody with a computer science degree or an electronic engineering degree can now do this kind of programming. So let me give you an example of the sort of thing that can be done with this and why I think it's important. And then I'll finish the talk by actually sort of talking a little bit about where the state of the art is, if you like. So here's an example. About 3 years ago, 2.5 years ago, I had a student, a master's student, using one of these boards, the one I've just held up in front of the camera, for doing a computation. It was called a stencil computation. This is a graphics processing, doing stuff to an image. As I said, these boards cost $100 US, maybe slightly more, and they've got I said it's an Altera Cyclone 5. Actually, or maybe I should say Intel now, because Altera have been bought by Intel, and it's got this ARM core on this standard microprocessor as used in mobile phones. And here's some results. Now, the thing I want to draw your attention to, I don't want to go through all of this, is that he got a speed up of about 16 times. If you can see my cursor's moving, that line there, 16 times. In fact, for some examples, he got a 40 times speed up. Now, what this means is that this was done on the board. The ARM processors are relatively slow. They're only 1 gigahertz. Okay, they're still very, very fast, but they're not as fast as the fastest microprocessors. So he got a speed up of 15, 16 times. So that's equivalent to a clock speed of 15 or 16 gigahertz. Okay, as I say, sometimes you got 40 times. If you could do the same calculation, the same scale up for the fastest possible Intel processors, that means you're doing something with the equivalent clock speed of something like 64 gigahertz. Have I done the sums right? 4 times 16, yeah, 64 gigahertz. So this is significantly faster in its computational power than a standard processor for something that costs $100, not a supercomputer, not something where there's a room full of computing equipment in an air-conditioned room. So these FPGAs are very powerful things. Now I've said, okay, we don't need an air-conditioned room, but actually that is what's happening. FPGAs are now being used in data centers. Microsoft are using them. Amazon are using them for encryption and decryption. So when you do a credit card payment, you're buying something from Amazon, the decryption of your traffic is probably being done on an FPGA, one of these devices in a data center somewhere. Intel, Microsoft are using these devices for artificial intelligence, self-driving cars, pattern recognition, that sort of thing. CERN are using these devices to search for dark matter, not actually dark matter as such, for the computations to search for dark matter. And so this featured a couple of years ago on a front page of a journal. I'm sure you all subscribe to this scientific computing world, but no, I'm kidding. But the point is that this is becoming kind of standard technology. So I said the title of this talk was A Supercomputer on Your Desk. So is this actually true? Well, I first wrote this talk for people, again, talking to a school about 2 years ago. And at the time I said, well, this is, technology that's coming. And about the time I was writing this, Apple made an announcement. And this is a quotation I've taken straight from Apple's website. So they've got something called an afterburner. It's a hardware accelerator card built with an FPGA, or what they call a programmable ASIC, with lots of cells and so on. They can do graphics processing. So that thing that looks like a cheese grater is in fact an Apple Mac Pro. That computer will cost you about $5,000–6,000. It's quite expensive. It's not the sort of thing you necessarily rush out and buy. The afterburner, the hardware accelerator, costs about another $2,000 US. So for about $6,000, $7,000, $8,000, that is a supercomputer, really beyond imaginable power. Maybe not on your desk, certainly under your desk. And I would bet, the Toy Story 5, Toy Story 6, whatever, things like that will be made using these devices, using this kind of technology. They won't be done using graphics cards. It won't be done using standard computers. Those sort of things will be done using a combination of standard computers and these FPGA technologies. And we're getting to the point where this is now going to be the technology that's used in all kinds of powerful computing applications. And so that's really the kind of theme of this, where we've got to the next generation of computers is this processors plus FPGAs. We can get clock speed ups of 15 or more times for relatively low cost. Even if you don't want to invest several $1,000s in an Apple Mac Pro, you can still get these kind of devices that will sit on a desktop. And I think it's very likely that within the next couple of years, you'll get these cards that will fit into a standard PC, or maybe it will be a separate box that plugs into the USB-C port of your laptop and gives you this kind of computing power. And it won't cost thousands of dollars, it will cost hundreds. Okay, so I'm going to stop there, and I'm willing to take any questions. If you want to scan that QR code, that will give you a link to information about the university. But I'm quite happy to take any questions about either what I've spoken about or about the university. I've lost track of what time it is.
That's great. It's 1:30, Mark, and that's
Oh,
great.
that's perfect.
Thank you for the chat. It's great. They are being very quiet at the moment, so the chat remains empty for the time being. So you're going to get questions from me for a little bit, and when they all get annoyed with those, maybe they'll add some more technical ones, because obviously a lot of the students here have some, pretty impressive technical knowledge that I do not have about computers. So I'm going to ask you some more broad questions, really. Mostly focused around careers, really, and that end of things. It's always quite important to us. And if anyone has a technical question about what any of that more powerful supercomputing capacity is, then do put that in the chat, and I'm sure Mark can tell you all about it and anything else. I think with obviously the kind of skills thing, I'm going to give you a bit of a quote. I've kind of been using this quote for a couple of years. And it's probably wrong. So I do like to test it on other computer science lecturers. I think this is one of your colleagues at Durham. And he sort of intimated that perhaps from an actual knowledge point of view, quite a large amount of what is taught on a computer science degree, by the time the student gets to industry, probably isn't used, because, as you pointed out, it's such a fast turnaround in technology. I mean, I think he said something like 70% of the course in terms of the actual core content. I mean, I think he just pulled that out of the air, but it was certainly more than half of the course. Obviously, we're looking at transferable skills more broadly, where obviously communication skills, that side of things. But what is it? What do you think you take away from the computer science degree that you take to industry? What part of it is kind of core knowledge, and what part of it is transferable skill, do you think?
Well, okay, so I think the first thing to recognize is that what we're doing is education and not training. Okay, and I think that's an important distinction that sometimes people don't realize. I mean, I don't know whether the 70% figure is correct, but it's sort of, whether it's 50% or 70% doesn't really matter. Obviously, things get outdated. Having said that, things like programming languages do stick around for a long time. I mentioned C and C++. I mean, C has been around for 50 years and people are still using it. C++ has been around for 30. I was talking to a colleague, I was saying that I was doing a bit of scripting using Perl. He said, isn't Perl dead? And I said, no, it's still going. There's a new revision came out last month. So a lot of the languages that the computing languages, the programming languages do stick around. But it's also what you learn is not, the syntax of the language, where to put the semicolons, that sort of stuff. What you learn is how to think in ways, how to break a problem down, how to analyze a problem, and code up that your solution in a way that is going to work. And I think that the best transferable skills, if you want to call them that come out of and it doesn't matter if it's computer science or engineering or anything else, is that ability to analyze a problem, to break the problem down, and to come up with a solution, and to think about where what the limitations of your solution are, how you can debug things, how you can improve your solution. I think any code that you write, it doesn't matter whether it's for a standard processor, whether it's for anything else, will contain bugs, and you have to learn how to debug things. You have to learn how to solve problems. Debugging a program is pretty much the scientific method, and the classic scientific method. You have a hypothesis about what the problem is. You construct an experiment to test your hypothesis, and if your experiment doesn't work, you try a new experiment. Okay, it's just the same as Galileo doing his experiments in the 15th century. The other thing that I think you get out of a degree like this is things like team working. We run group design projects for people doing the 4-year degree. So we had, across the whole school of electronics and computer science, we had something like 230 students this year in the 4th year doing projects. This was broken down into teams, about 60 different teams, 4, 5, 6 students in each team, doing projects with companies, industry-inspired projects. Some of these projects were really demanding, doing things like machine learning, doing things. I'm trying to think of other things that were involved in communications devices. Again, using these FPGAs and things as for analyzing network traffic. To see whether there's bad traffic and things like that happening, and so those sort of skills of working with a team and communicating what you're doing with a customer are things that you would learn in the course of a degree, and those are transferable. And you could say, well, you can do that in an abstract way. Why do you need to know in a computer science degree? But it is focusing on those particular problems, learning how to think about things in particular ways, and I think that's one of the things that you would get out of this, an important aspect of this.
That's brilliant. Just on, I guess, sticking on that, in terms of where students go on to afterwards, that's something I think that often comes up. I mean, I was going to say, you mentioned that company ARM earlier. I guess, I assume, and this is from talking to the students who are interested in computer science, obviously, I think you could probably predict the type of places they say. There's a Google, Apple, etc. No, I guess,
absolutely.
For want of a better word, kind of sexy destinations. Are they still the ones that your students come on wanting to do? Or actually, once they're on the course, do they find actually there are these niche things or other things that once they've got a bit more knowledge that they do want to go into? Or is that still the apex, really?
No, absolutely. I mean, there's a whole variety of things. I mean, one of the things I will say to start off with is that the employment statistics for our programs are really, really good, amongst the best in the country. Now, how you measure these things is always difficult because it's done by surveys, and we all know, I'm sure we all get lots of requests to participate in surveys, and most of them we don't respond to. And so we survey all students 6 months after they graduate to find out what they're doing, and the response rate is not particularly wonderful, but 90-something%, 92, 93% are in graduate level jobs 6 months after graduation, or they're going on to do further studies, and that's very, very impressive. I could give you a quote, but it will take me too long to find it, of something I had from a company just a couple of days ago, saying, praising, I don't know what the company was, but praising a particular graduate from Southampton, saying this is typical of Southampton graduates. Anyway, but you're right. I mean, students go to companies like Apple, Google, whatever. The company I mentioned, ARM, who do all this processor design, I think we probably have about 10 students a year, which doesn't sound a lot until you sort of think, well, okay, that's probably 5% of the graduates, but actually they don't take on that many students. They sell a lot of designs, they have a big turnover, but in terms of engineers, they're not particularly big. But you also find people going to more general engineering companies, BBC, BAE, and then other manufacturing areas. So people will go and work for food companies or whatever, things like that. And we have a number of students who start their own companies as well. We have a very Southampton has a really good record for spin-out companies, among the best, not only in the UK but in the world. Now, obviously, spin-out companies don't have 100% success rate. I mean, that's the the nature of the business. But a lot of students do start off by, there's opportunities to develop ideas. There's well, there's one of the screens I'm actually using is something that some students tried to develop as a project. It wasn't successful as a project, but it actually makes quite a good screen for the second screen for me working at home. So they can get investment in things. We do a sort of Dragon's Den type activity. So some students, really want to work for themselves, start their own companies as soon as they graduate. Some students would much rather work in a larger company. So it's whatever you want to do, really. The opportunities are all there. We try and have lots of links with companies, and these fourth year group design projects are, from the company's point of view, very often a really good recruitment tool, because effectively what they're doing is interviewing a student over, or a group of students over a period of about 10 weeks, which is a really good way of doing an interview. And students often have internships and so on, and will work for a company in the summer or whatever. And again, if you like, that's an interview that goes on for 4 years. And so, yeah, there's also, basically, yeah, you can do whatever you want. Having said that, of course, some students graduate and just go off and do something completely different anyway. They go and work in the City of London or somewhere. Again, you're coming out of this with a degree that is numerate, I guess literate to some extent, because you have to write reports and so on. But that sort of technical basis is actually a quality which is recognised in areas beyond technology as well. And so any kind of technical degree you can look at it as a good grounding for other things.
That's just in terms of, this might be a bit of a novice question, but so I'll put it to you anyway. In terms of over the next 20 years, do you think that kind of solid employment rate will probably stay the same? Obviously, we're talking about the development of the technology. I suppose, is there a counter argument that some of it will become more accessible to just the layperson? For example, making a website, which is now relatively easy, but 15 years ago was reasonably complex.
Well, to some extent, you're right, because that whole sort of Apple thing and so on. Yes, it is. From going from having to use a specialist textbook, to doing stuff that you kind of just adapt the programming skills. Yes, I think that is happening. But on the other hand, technology is advancing in ways that will always be a challenge to people. There's been a lot of talk about things like quantum computers. Now they're okay, they're very specialist type things. I'm a bit of a skeptic as to whether they're ever really going to deliver what they promise. But on the other hand, they're not things that you can program in the same way. And there are other technologies, so there'll always be those specialist skills needed. I think as long as the underlying technology continues to develop, the skills needed to use it will still be needed. The cutting edge technologies are never going to be consumer friendly. So yes, I think, but I think it also means that I'm trying not to get off into a long discussion here, try and make this simple. One of the things we have to teach as a university is what's called continuing professional development. In other words, we need to, one of the things that you should get out of a degree is a sort of mindset on continuing to study. You always learn for your entire professional life. You will carry on learning. You will never stop and sort of say, right, I know enough. That's it. I can just coast for the rest of my life. There is an expectation from professional bodies that you spend 30 hours a year on continuing professional development on education. The 30 hours is nothing. I think probably you ought to put an extra 0 on that. But that's what it means. You just have to keep on learning. And so one of the things we should try and do as a university, and we do try and do, is to set students up so that they have that desire to carry on learning, but also the I guess the sort of self-discipline to do it, to always keep ahead of things, to read the technical journals, to keep developing.
Can I just, on the technical stuff, I think this gets asked a lot for anything that's tech related, is the kind of skills on entry. And then obviously you mentioned the sort of coding and any kind of computer languages. And I think it's often asked, how much would you need, or how much is it useful to know going in? And just to add to that, also just the level of mathematics. I mean, most of our students will be applying with A-level maths and often with further maths too. But it's just how much is maths a driver of the program that you teach?
Okay, so the answer on maths, there's two aspects of that. One is that mathematics, when you're doing mathematics in school or whatever, it teaches you beyond the mathematical skills themselves. It teaches you a way of thinking, a problem-solving approach. And that way of thinking is very useful and very important if you're doing computing or anything like that. As I said, when you're debugging a program, you're using science, you're using the scientific method. Okay, so the way of thinking that you learn by doing mathematics is important in computer science. And so therefore we, Southampton, asked for a mathematics qualification because it is an indicator of, if you like, somebody who's got a logical mind, who is good at problem solving. Now, there are programs where you don't need strong mathematics skills on entry. And as I said, I think, I would draw the distinction between education and training. So I think if you want an education in computer science or engineering or areas like that, you need that mathematical way of thinking, that logical way of thinking. If all you're interested in is training, then maybe that's not quite so true. That's one side of that. The other side of it is that there are certain things now, certain aspects of computer science that do require quite a strong mathematical underpinning, particularly things like machine learning, artificial intelligence. A lot of it is based upon statistics, and I think it's true to say most people find stats difficult, okay, because it's not intuitive. But a lot of the machine learning stuff is pretty heavy mathematical stuff, and if you don't get that and you can't do it, those kind of careers are really out of reach to you. So I think you need it if that's what you're interested in. If you're interested in going into some of the more cutting edge kind of things, then you do need those mathematical skills. You may not be applying calculus, differential equations to programming, but as I say, it's the way of thinking. It's the basic knowledge that is important. And we ask for quite a high, I think, I can't remember off the top of my head, but I think we ask for at least an A in maths at A level, if you're doing A level or the equivalent.
Yeah. Okay. And with the languages, just because you brought it up earlier, I think
sorry,
yeah, a lot of the thing. Yeah, is that something as well?
No,
I mean,
that's not so important.
Is that a preference, or is that
we don't? It's useful, but not necessary. We don't really make any assumptions because, because people, I guess, if you've done it as a hobby, or if you've done it as done a computer science A level, it's helpful. But if you've never done it before, if you come in with kind of, if you like, maths, physics, chemistry, you could still do a computer science degree, even if you've never programmed a computer or done any kind of programming at all. We don't make assumptions on that basis coming in. As I say, it helps, but it's not necessary.
That's fantastic. Well, just draw it to a close now then. With I know you've got a head off as well, Mark. I'd normally end on sort of talking about the future of the industry and that side there. I think it was kind of implicit in your talk anyway, because you're kind of talking about development and the cutting edge of technology and that side of it. I suppose one element I am quite interested in, and this comes from the kind of World Economic Forum and their thing, that all jobs and all roles will need going forward, and that's the sustainability factor. I think it's particularly interesting in this industry where that comes and where it doesn't, particularly where there's where it's all about development. What's your feelings about that, and is that in any way incorporated into the Southampton course?
So one of the things I think is worth mentioning is that our degree programs are accredited by professional bodies, okay, which ultimately go back to the Engineering Council in the UK. And the Engineering Council has put out a new set of guidelines which will take effect in the next couple of years. And I know a lot about this because I'm kind of involved in accreditation, on behalf of some of these bodies and going to other universities. And some of the things that are coming up are things like sustainability, but also, as I mentioned, continuing professional development and all of these sort of, the things that are not directly technical things to that discipline, but more general, such as, as you say, sustainability. So that's an important part of doing a program. Now, as I said, we're a school of electronics and computer science. It's sitting in a faculty of physical sciences and engineering. So actually, we do regard computer science really as an engineering discipline. And so therefore, all of these things such as sustainability and so on are important to the program. Now, in the context of computer science, what does sustainability mean? Well, I mean, just to do a very, very quick, in just the last couple of minutes, you'll all have heard of Bitcoin. Bitcoin is, Bitcoins are mined. Actually, people use FPGAs for mining Bitcoins. The amount of electricity being used to mine Bitcoins is greater than that of many small countries. It is a ridiculous amount of energy, and is really not justifiable. The whole thing is, frankly, in my view, a scam. But the power, the energy thing is useful. The reason why many of the top 500 supercomputers use graphics cards for computation is electrical energy. It's the cost of the things. And indeed, going back, I could have spent another 5 minutes talking about this. I said supercomputers sit in air-conditioned rooms. The cost of the electricity for the air conditioning might be greater than the cost of the electricity for the computers themselves. Okay, so you get people building supercomputing centers in Alaska and places like that where it's cold because they get the air conditioning for free. So all of these things are important, and Google and whoever talking about going kind of carbon neutral in the future, and to some extent, I think that may be social responsibility. But on the other hand, they also recognize that the costs of electricity for what they're doing is so huge. They need to find other ways of doing this. They need to start building their own wind farms, or solar systems or whatever. And those are intrinsically, I guess, more sustainable than fossil fuels or whatever. And I mean, personally, I think the more that we can switch to electrical things anyway is more. I saw something yesterday saying the cost of a petrol or diesel car is significantly greater in environmental terms than that of an electric car. So the more stuff we turn into electrical things, the better it's going to be, and that's important. And the more things that are electrical, the more they rely upon programming and processors and computer science and so on and so forth. So I think it's difficult to talk about sustainability when you're talking about writing lines of C, but if you think about it in the bigger context about how things fit together, I think it's an extremely relevant question and something that we do need to think about. And also, I of course, if you're going to have wind farms or whatever, the control of the systems themselves and the load balancing within the grid and all the rest of it. If everybody comes home at 5 o'clock and plugs their electric car in to be charged, it's going to cause a surge on the grid. Things are going to break down. That requires artificial intelligence, computer science, whatever, to control the load, and to some extent to encourage people to charge their cars when electricity is cheap. The whole thing is interlinked. So I don't, sustainability is a really, really important part of this, but perhaps in ways that are not directly obvious.
Great. Well, listen, thank you for joining us. I know you've got to shoot off because you've got lots of other meetings to get to. You're only just starting your day there as we're ending it. Listen, it's brilliant to have you on. I think it was a fascinating talk. They were quiet, but I know everyone would have got a lot out of that talk, and there would be a lot of interesting things. I think obviously we have a number of people that have crossed over, in software engineering and various things that have gone over through these talks. But I think there was some actually really quite original and interesting thinking, stuff that we haven't covered before from lectures and other things. So I really appreciate that, Marcus. Really good talk.
Well, thank you for attending, and thank you to the. I'm not sure how many students it were. I think it was about 9 or 10 students.
10 or so,
attending.
yeah, in the end.
Yeah. So I'm not actually offended by the fact you didn't ask questions. I've given this talk probably about, I'm not sure, several times in the past couple of years, and actually I have found the question, people have been quite quiet because I'm throwing a lot out there. So don't worry, you're not different to the other audiences. So either I'm doing something completely wrong, or it's a typical reaction. Anyway, so thank you for attending, and if you'd like me to repeat it at some later stage, please ask.
Yeah, you're more than welcome. We'd love to have you back. Okay, well, Mark, thank you for coming. We'd like to say goodbye to you now. If you want to leave the meeting, you can. See you later.
I'll do so.
And you
I
get
need to
some
go get a
thank
drink
yous
of
there.
water, I think.
Yeah, I think so. I will
Okay.
stay around, and Ms. Shazza will stay around if any of you want to ask me anything or work anything out. So if not, please also leave the meeting too. Mark, thank you very much for coming.
Okay, cheers. Bye.